that can't get in right now, you could also watch this on YouTube later, so you can still do the activity. No, I don't have to see the coins. So I'm answering people in the chat. I don't have to see your coins, but the idea is that I wanted you to do something hands-on today, something a little bit different. I know you all probably are getting antsy because I'm definitely getting antsy. And that was just, this was a way for us to model and make it easier to understand the concept. So it's more like I wanted you to do this with me together from home if you could, but I understand if you can't. And that's why I mentioned in the comments you could make this up using paper. So the chat needs to stop now. If you have a question, please post your question in the chat. I can see everyone's chat, so we're gonna stop using the chat to talk back and forth. Miles, I've answered your question on Google Classroom. And anybody that continues to make jokes on the chat, I'm just gonna remove you and I can exit you out, and then it's over and you won't get credit for today. Please participate the way that I've asked you to. Otherwise, this ruins the experience for everybody else. Okay? If you don't have 100 coins or you haven't cut out pieces of paper today to represent our atoms, then you can just follow along with me as I do this here in front of you guys. Everyone should also be on Nearpod. So I'm heading over to Nearpod now for our lesson. All right, I'm also tracking your participation on Nearpod. So if you're not on Nearpod, I'm not going to be able to give you credit for doing the work today. So I got 25 people in Nearpod. I should have everybody there. And again, your participation on Nearpod is counting for your credit. So thank you guys. Again, if you can't participate on Nearpod, I'm going to post the video where I'm going to share my screen for Nearpod. I just need some sort of proof or just communication that you've watched it later to count for today if you're not able to participate. All right. Are we all ready? So I got 34 on Nearpod. I know a couple people can't join based on what they're doing right now, but thanks for still showing up and we can figure this out. Like I said, you can watch the YouTube later to help navigate, and I can send you the work that you would have done on Zoom. I'm sorry, on Nearpod. All right, so I'm gonna get moving. I got a couple more people to join, but you can join us when you have a chance on Nearpod. All right, so on Nearpod, you should see, I'm gonna share my screen now. On Nearpod, here is our lesson for today. So you should have the materials I've listed. So it says, today we'll be conducting a lab activity to model how radioactive isotopes decay. By modeling this process today, we will have a better understanding of how radiometric, aka radioactive dating, is used in geology to date rocks and fossils. You are going to use 100 coins, or you're going to be watching me. If you're using the coins and you're doing this with me at home, you just need a workspace for this. We're going to be dumping the coins out onto the table and then counting how many are heads up and how many are tails. So you want a good space to be able to do that. I'm using my coffee table, which works just fine. You also want a piece of paper. So if you're at home and you're not doing the coins at home, please have a separate sheet of paper, because I'm going to be reading off to you the data, and that you can use that to answer the questions in Nearpod if you don't have this on your own at home. Okay, so a separate sheet of paper and something to write with. And again, if you're using the coins at home, I'm using a cup that I'm going to put all of my coins back into each time. A cup / tennis ball holder thing. All right. So again, if you're not doing this at home, have a separate sheet of paper and a pencil to take notes and write the data down as I do mine here for you guys to use. Okay. You can use a bowl. That's fine. Absolutely. All right. All right, moving on. We are going to start out today with a video to review what radiometric or radioactive dating is, how it's done. So you're going to watch this on your own device. So I'm going to play that now. A box or a bowl is absolutely fine. Yes, I'm using this tennis ball holder thing, but absolutely you can use anything that can just hold coins or hold these things to be shooken up and then dropped on the table to separate. All right. All right, so now everyone should be on the video again covering how radiometric dating works. And this is going to be a good reminder or review as we're about to demonstrate this today in our lab activity. So here we go. Go ahead and watch. I'm going to go ahead and mute myself so that you guys can listen to this on your own at home. All right, everyone. So a lot of you guys are communicating that you finished, which is great. So take in mind a couple of things that he said. So he said that there's multiple types of radioactive isotopes that can be trapped in rocks that we can cross-reference, meaning, remember, scientists are cautious. So we do not want to say or conclude something. We do not want to form a conclusion unless we have a lot of data that supports it, meaning that we want to be sure, right? So if you have something like that's within the last 50,000 years and you can use carbon dating, okay, you might also use uranium and count the uranium isotopes in the rock as well, because the numbers of the decay rate should be the same. And if they are, then you have more confidence, of course, coming out. So when he was talking about the zircon crystal from Western Australia, that zircon crystal was 4.4 billion years old. But they showed you that they used multiple isotopes to confirm that. In that process, there's another video about that I haven't showed you, but that specific zircon crystal, they spent 10 years counting the atoms, every single one, and then counting how many had decayed so that they were absolutely sure, because that is the oldest rock in the world. So if they were going to come out publicly with the entire world science community and say, hey, we found the oldest rock in the world, they wanted to be absolutely sure down to every single atom. So it's pretty fascinating that they did that. And of course, very confident that it is the oldest rock, meaning it's 4.4 billion years old. Our planet's estimated to be about 4.54 billion years old. So that was really surprising to many scientists that a hard rock could have formed that early in our Earth's history, knowing that Earth at that time was mostly still liquid, right? Because of all the heat and the liquid rock that was making up our planet at the time. So we had a tiny little bit of crust starting to form that early at 4.4 billion years ago when the zircon crystal formed. All right, so on to our actual activity. The oldest one is Australia. So depending on the videos you watch, like this video that I just shared with you is only 1 year old. This is more up to date. So the one that was found in Western Australia is older than the one found in Newfoundland. So before the Australia one, Newfoundland had the oldest, but this Australia one is older. All right. For this activity, this is going to be our lab for today. So I included the introduction to the lab on this page, and I'd like you to read this, please. There are 2 places to fill in blanks, and you can write them in or type them in the blanks on the page. So when you read the introduction here, this should just take a few minutes. You're going to write in or type in your responses. For some of the people that are messaging me that they're not able to do Nearpod today, remember, I'm recording this video now for us so that I can upload this later to YouTube. If you're not able to participate with us, maybe by watching the video, you can write your answers on a separate sheet of paper so that you can still show proof that you did this with us. So when we talk about what this is called, this absolute dating method, some people say radiometric, like the title of this lab. Some people say radioactive dating. Either one would be acceptable for this method of counting the isotopes that have decayed in a sample to determine the age of the sample. So either radiometric would be correct, or radioactive. Carbon dating is just super specific. That would mean we're using radiometric dating with carbon. So when someone says carbon dating, they're usually meaning the same thing. It means that they're specifically using carbon. In today's lab, we are going to be using carbon. So today, our pennies are representing carbon-14 atoms, and we're going to model half-lives, meaning how long it takes, right, for them to decay. So today we're using carbon. Nice job, Alex. And so that's acceptable today, but just understand that when someone says carbon dating, they mean this method, but they mean specifically with carbon. Anything that's older than 50,000 years, we have to use something else. Usually we turn to uranium. There's 2 versions of uranium. There's uranium-238 and uranium-235 that you can use. The half-life of uranium-238 is 4.5 billion years old, which is almost the length of Earth's history, right? So we can use uranium-238 not just for things on Earth, but also meteorite samples that are even older than our planet. at around 4.6 billion. All right. Something else that he mentioned that I wanted to bring up was he said we can't date sedimentary rock using this method. And that's because the sediments that make up the rock were formed as igneous rocks at some other time. So sandstone is really hard to be able to date because you're not going to get you're not going to get an answer of when the sedimentary rock formed. You're going to get an answer of when the sediments in it formed, which is different. But you can use index fossils that might be trapped in sedimentary rock, right? So I don't know how old the sandstone is, but if it's trapped and preserved a fossil of an organism in it, we can date the organism, and then we know how old the rock was that encased the organism. It's okay. There's also text. You can also put text in instead of handwriting it, which I know is hard. So you can put the text in instead of having to handwrite it. All right, so I've got to keep moving on for sake of time, but you guys are doing great. So the first answer should have been either carbon dating, radiometric dating, or radioactive dating. The idea is that this name is describing the process of counting radioactive isotopes to determine the age, absolute age, of a specimen. The second answer to the fill in the blank was half-life, right? So a half-life is the length of time it takes for half of the isotopes to decay, all right? Now for carbon, that's exactly 5,730 years. It takes 5,730 years for half of the carbon-14 in a specimen to decay. What does it decay into? Nitrogen. Okay, so we're gonna use coins today to model this process. All right, every time I flip my coins, that's representing one half-life. This works out really well with coins or any two-sided objects because it's a 50-50 chance, right? So if I pour 100 pennies onto my table and I count how many of the pennies landed heads up, right? It's gonna be about a 50% chance, meaning about 50 pennies should have ended up heads up and about 50 pennies will be tails. Now, it's not gonna be perfect, but I promise you that if we combine all of our data together, we would end up with an average of 50-50, right? So this is chance, but at the same time, on average, right, we should end up with about 50-50. All right, so again, going through this, our problem for today in our lab is how long will it take 100 atoms, and again, today I'm using 100 coins, of the radioactive parent carbon-14 to completely decay into nitrogen-14. In today's activity, I'm going to put all of my 100 pennies into my cup, and any of my pennies today that land heads up are representing carbon-14 that hasn't decayed, okay? Any penny that lands tails up, or any coin that ends up tails up, is representing a penny that decayed. In this case with carbon, it turns into nitrogen. All right, so again, my problem is how many, meaning how long in regards to number of flips is it gonna take until I end up with all of my pennies tails? Every time I get a tails, I'm gonna push it to the side and I'm only gonna keep the ones that were landed heads up. I'm gonna shake it again, I'm gonna pour them out. I should once again have 50% of my sample that should have decayed, meaning ended up as tails. I'm gonna put the tails to the side, keep the heads, flip those again, and eventually we'll see how many half-lives pass until all of the carbon has decayed. Meaning how many half-lives does it take for all of the isotope to decay? All right? All right, nice job. If you don't have 100 coins, then it'd be a lot simpler and it would last a lot shorter, but you could use like 50 coins or 10 coins, and the idea would be recognizing that flipping is representing a half-life. So if you don't have 100 coins, then you could definitely do this with less, but just remember that 2 coins is representing 2 atoms. I'm sorry, 1 coin is representing 2 atoms if you're doing 50. Yeah, so the idea is you should count out 100 coins if you're doing this at home. to represent 100 atoms. So if you haven't done that yet, go ahead and do that now. All right, so here is our procedure for today. So this is what I'm going to be doing at home, and this is what you'll be doing if you have these coins at home. And it says radioactive decay using coins. All right, so it says we're going to start with our 100 coins. So I have mine here. Every penny is representing an atom of the radioactive element carbon-14. So as soon as something dies, 100% of the carbon-14 it has is intact, right? You guys with me? Nod or give me a thumbs up. So when something dies, all of the carbon-14 stuck in it, right, just got there, okay? So this is marking the beginning of a rock or a fossil, right? And at the beginning, it has 100% of the carbon-14 that is trapped in it, okay? One dump of my coins is going to represent one half-life. So it says for step 2 in our procedure, it says dump out all the pennies and spread them out on the table. Remove all the coins that show tails. Anything that lands tails up is going to represent a decayed atom. And in this case, it's turned into nitrogen. I'm going to push all my tails to the side. All right. Then I'm going to put in the ones that landed heads up. I'm going to shake and I'm going to flip again. This represents the second half-life that is passed. Now, from yesterday, you should remember, after 2 half-lives, you should end up with only about 25% of the parent isotope left, meaning 75% of it has decayed, meaning broken down and turned into nitrogen. All right. Blaze, are you still counting? Okay. Riley, are you doing this at home? Riley, are you doing this at home? Have you counted out 100? Awesome. Okay. All right. So I know most of you aren't doing this at home, but I'm just waiting on the few that are so that we're all doing this together. All right. So again, 100 pennies is representing 100% of the carbon-14. Okay, awesome. Alice, do you have 100 counted? Cool. All right. So again, this is representing all of the carbon-14 at the beginning of the end, if you will. So think about this like this is a fossil of a dinosaur. It's going to start with 100% of its carbon-14 atoms and isotopes are intact. Okay, we're going to represent one half-life, the first half-life now. Okay, so with your 100 coins, you're going to shake them up, and then I'm going to put them on my coffee table, and I'm going to spread them out. All right, so I'm going to spread out my coins. All right, and I'm going to count, and this is where if you're at home, you're going to write this number down on a separate sheet of paper for me, and this that I just did is representing a half-life. If I was being super specific in modeling, then I would actually count how long it takes me to count out how many were heads up, because that could represent the length of the half-life, right? So our half-life is the amount of time it takes for half of the atoms to decay. So I'm modeling that here by dumping coins out on the table because I know that about 50% of them are going to be heads up, representing one half-life that's passed. All right, I'm not going to count how long it takes me to count them today, but know that that would be the length of the half-life. I'm just going to count how many of my atoms have landed heads up. I can easily do that, and again, if you're at home, just separate any that are tails to one side of your table and any that are heads to the other side of your table, and that will make it easier to count them at the end. So I'm putting all my heads to one side and all my tails to the other side. Bear with me, I'm almost finished. All right, I'm almost finished. So what I should end up is a pile with all of my heads up pennies and a pile of all of my tails. All my tails are representing the decayed atoms. All of the ones that are heads up are representing carbon atoms that have not decayed yet. All right, so here I go. I'm going to count my heads up. Okay, this is the number of pennies that are heads up. This is representing one half-life. So here I go. One, all right, it's easier to count coins by twos, so I'm gonna count by twos. Saves me time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, whoa, 52, 54, 56, 58, 60. All right, well, that's chance for you, right? When it comes to odds, I was probably going to have about 50, and I ended up with 60. And that's just because it's, you know, random. Nice. Oh, I'm so excited. You got exactly 50, Jaden? That's awesome. All right, so yeah, so this is chance, right? So it's always a chance that I could get a different answer, but on an average, when we combine all of our data together, then we should still end up with an average of 50, right? Some might get lower than 50, like me, some might get higher, but mine was, again, 60. So I had 60 heads. So for my first half-life, the number of pennies that were heads up was 60. All right, so for half-life 1, meaning one half-life is passed, I had 60 left. All right, so what I'm gonna do is I'm now gonna take all my tails that I counted out, and I'm gonna put those to the side. They've decayed, they're done, right? So this would be like carbon-14 atoms that turn into nitrogen. It's over, okay? I'm gonna now take all my 60 heads that are representing, see, look, Riley got 44, I got 60, but if we average these together, we get closer to 50. All right, so I'm gonna take all my pennies that were heads up, I'm gonna put them back in my cup. I wrote down that I had 60. All right, and now I'm gonna do it again. I'm gonna put them all into my cup. Nice. Hey, Trent, if you're using 50 and you got 22, that is about half, so good job. So obviously for anyone that's not using 100 pennies, this is gonna go a lot faster for you than it is for me, but you understand it's just the math, right? So I'm gonna do this again. I'm gonna separate them all out. I had 60 to start with. There's a 50-50 chance. Half of 60 would be 30, so I should have about 30 that end up heads up. So let's see this time what I have happen. I'm gonna separate, put my heads over here, put my tails over here. This is bringing me back to the days when I had to count registers in college. All right. I got the fresh pennies. I went to the bank, gave them $1. They were like, "You want 100 pennies?" I said, "Yes." Okay, here we go. All right, so let's see. It should be around 30, but here we go. So I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. All right, I got 34 this time. Again, higher. This was representing 2 half-lives have passed. Okay, so if you look now at my table, over here, I've got all my decayed pennies, which are acting as the new isotope of nitrogen that has formed from the parent isotopes of carbon-14. All right, I'm gonna keep my 34 pennies now. I'm gonna do the same thing again. Now I'm going on to half-life number 3, right? So I'm gonna take all my heads up pennies, I'm gonna put them back into my cup. And now this would be what's going on. This is how much should be left in the sample for 3 half-lives. Riley, nice. Okay, I'm gonna go ahead and pour. You're writing this data down because in a minute we're gonna have another collaborative board where you're gonna write your answer, draw it into the table. So if you're using my data, I'm gonna give it again to you. All right, so that way, don't worry if you're at home and you're not doing this with me. I'm gonna give you my data so you can use that for the table. Okay, so again, I'm gonna move all of my tails to the side. I'm gonna put my heads to the other side. I know this is tough if you didn't have coins to use, but again, if I want you guys to do labs, I'm going to try to give you notice like I did yesterday where I posted it the day before. And if you can't do it, I understand. It's just a little more fun this way, and I know we're all probably a little antsy, and I wanted to do something hands-on today, so if you can't, I understand. Okay, so I'm gonna go ahead and count up. This is my third half-life, okay? So when we're considering how much of a sample should be left after 3 half-lives, it's around 12.5%. Okay, so after 1 half-life, 50%. After 2 half-lives, 25%. After 3 half-lives, about 12.5, right? So let's see what I have. 2, 4, 6, 8, 10, 12, 14, 16, 18. I keep getting really high numbers. All right, so I got 18. Again, all of mine have been a little higher. Avante got 13. Nice. Blaze got 11. Nice. All right, so perfect, right? So we're all around what would have been 12.5. So again, if you have a rock, so now let's bring this all together. You have a rock, and again, these pennies are representing isotopes, and you have about 12.5% of the sample is carbon-14, and the rest of the sample is its decayed version, right? Then you know that 3 half-lives have passed, which means that whatever the sample is, if it's carbon-14, 1 half-life for carbon-14 is 5,730 years. If 3 half-lives have passed, I just multiply the length of the half-life by the number of half-lives, 3, for my answer, which is around 18,000 years old. All right, so I'm gonna go ahead and do this again. The idea is we were gonna do this until all of them are now decayed. So I had 18 left for my third half-life. I'm moving on to half-life 4. I wanted you guys to hypothesize. So if you haven't done this yet on the near, you have it obviously because I didn't pull it up. I'm going to pull this up here. So now on Nearpod, I want you to hypothesize. How many half-lives do you think it will take for me to finish? So right now, I've done 3 half-lives. I've got 18 left. How many more flips do you think it will take altogether for all of them to be gone? And remember, carbon-14, oh, it's so great to see you guys all participating. Thank you. So for carbon-14, you can only use that isotope for something that's under 50,000 years because, like you're seeing now, there's not going to be enough left of the sample to reasonably be able to find it to get an answer. Does that make sense? Because after a while, they're all going to be gone. So you can't use that method anymore for something that's over 50,000 years. Okay. All right, I got some answers coming in. You guys are awesome. You said 3. I've already done 3, and I still have 18. So I'm going to keep flipping, moving the tails to the side every time. I want you to guess how many you think that it's going to take altogether for me to have all of them flipped. So I've done 3 flips. I still have 18 left. So how many flips altogether do you think it will be? So your answer's got to be more than 3 because I've already done 3. I realize some of you are saying maybe 2 more to make 5. Okay. All right, remember we all should be participating on here. Nice. I think most of us have. All right, so I'm gonna go ahead, I'm gonna keep going. Remember, I'm tracking this on my sheet, and in a little bit, we're gonna put this all together on ours. So I'm gonna take my heads up. I had 18 left for my third half-life. I'm gonna put them all in my cup. We're gonna keep going. Shake it up, I drop them, I separate them out. I now have, whoa, got some different results this time. I got a bunch of tails this time. Wow. And shake enough. All right, so here I am. My fourth half-life, I've only got 5 with heads up, and the rest of them were tails. So that means I only had 5 left, and that means that I should have 13 because I had 18 to start. So 2, 4, 6, 8, 10, 12, 13 ended up as tails. I'm gonna put these to the side. So 5 out of my 18 landed heads up. So I've only got 5 left. That was my 4th half-life. So I'm gonna go on to a 5th half-life. I'm gonna put it out. All right. All right, so I ended up with 1, 2 landed heads up after 5 half-lives. So I got to keep going. So my tails go to the side, 2 left. Both landed heads up. Moving on to a 7th half-life. Dang it. Heads up. This is why you shouldn't gamble. Okay. 1 left after 8 half-lives. Heads up. Tails. All right. So how many did it take me until all of the carbon was gone? You guys can talk now. Oh, sorry, I meant to unmute everybody. All right, everyone.
6.
How many times did it take me until all of mine were gone?
It took me 6.
10.
Yeah, I had to go all the way to 10. All right.
Can you show us your
All right, so some of you guys got it in a lot faster. Some of you guys had like 6 half-lives. But I hope that this is helping you kind of put this all together. I don't know what's wrong with my pennies, or maybe it's just my cup I chose, or it's just chance. But again, let's move on to the next question on near. So, all right, so on this part, it said how many coins landed heads up, and this was after the first trial. Writing the same to me, so after 1 half, this page, I want you guys to write how many landed heads up. If you did this at home, I'm going to go back to muting everyone. If you did this at home, you'll put your
Miss Ryan, you muted yourself.
You're going to be on the computer. You're on mute.
Miss Ryan.
Can you show us your notebook?
Yeah, you muted yourself.
No, she muted herself.
Hi, guys.
All right. Sorry, everyone. Now you can hear me and we can hear each other. Okay. All right. So it took me a total of, for this part, this question on Nearpod said how many coins landed heads up. And this is supposed to be after the first half-life, which for me, the answer was 60. If you did this at home, then you would write whatever your answer was from half-life number 1. Remember, after 1 half-life, you should have about 50% should have decayed. And for me, my answer was 60. So if you're following along with me, your answer here on Nearpod, you would type in as 60. If you did this at home, like Blaze, Jaden, Alice, Riley, any of those that did this at home, you'll write in your actual answer for how many landed heads up after 1 half-life. So go ahead and write answers in on Nearpod. Nice job. All right, thanks everyone, nice job. Can you give me a little bit of feedback? Give me a thumbs up if this made sense, and honestly, give me a thumbs down if you're like, ah. So I'm looking for a thumb up if you're following along with me. All of this activity was representing atoms, specifically isotopes that are unstable, and they break down, nice, and they break down, right, over a fixed amount of time. All right, so again, a half-life doesn't change. So carbon always takes 5,730 years for half of the atoms to decay, which is amazing because that's the only way we've been able to date anything with confidence and find out exactly how old it is. All right, perfect. Moving on to the next one. All right, so again, we already finished this together. It said continue your lab procedure until all of the remaining carbon atoms have decayed. So I'm going to skip to the next page. All right, so again, I wrote these answers down on a separate sheet of paper, so anyone that weren't able to do it with me. So I'm going to hold up my paper if you can see it, but you're going to write your answers in for the half-lives and the number of your pennies that landed heads up representing undecayed. There's also the top here that says experimental design. So we talk about our independent variable, that would be in this case our flips, and then our dependent variable was the number of coins that landed heads up or tails down. All right, so if you're writing these numbers into the table of the results, then you can use mine if you weren't able to do this at home. And kind of when you're putting this all together, keep in mind that once there's not very much of the sample left, like when I was down to 1 or 2 coins, that's why we say for carbon 14, once you're past about 30 or 40,000 year old for a sample, there's not really going to be enough carbon left to reasonably be able to figure out how old it is. And then eventually it'll all be gone. It will all be decayed. So you can't use it after a certain amount of time. Meaning once something is so old, it's not going to make sense anymore. Yay. Yeah. So carbon, think carbon, young stuff, awesome. But once something's too old, there's not enough atoms left to find to be able to count to figure out its age. So we have to use things like uranium-238, which has a half-life of 4.5 billion years old. Yeah. Of course, I'm happy. Please try to check into Google Classroom when I post stuff about a lab, just so you can have a heads up to get it together. Ow. So when we talk about experimental design, remember your independent variable is the thing that you have control over. The dependent variable is the thing you're recording. So in this case, every time we recorded the number of heads up pennies we had representing undecayed atoms, the number of flips we did was in our control. All right, for some of you that are communicating to me, thank you. I see what you're saying, and that's okay. Just do your best. Remember that tomorrow is our last day before we'll go on spring break. So we're still planning to honor spring break, meaning we won't have class all next week, including Monday of the following week. And then we'll go back to online learning. We are very fortunate that we can do this. There are many teachers I know in other states who are preparing to have to go back to school over the summer if they can't find a way to do online learning. So remember that you being here is helping you and I so that we can finish our school year at the regular time. Of course, it's not ideal, but I think it's awesome that we're still doing this. No, this technically still counts as part of this quarter. So our quarter officially ends tomorrow. Your volcano research journals, by the way, are so awesome. So I'm in the process of grading those. Those will go up. Please be patient with me because I'm trying to plan labs and activities and also grade. I'm also not really good at working at home. I'm incredibly distracted. So I like being at school better. Yeah, they're awesome. They are really honestly the most creative I've seen. I don't just say that. They are honestly the most creative I've seen. So it's really special. Okay. So many of you are finishing this last page. It's 12:21, so I'm going to have us end here. We might talk back about this tomorrow to finish our lab tomorrow, the follow-up questions. You guys did a great job. So awesome. The chickens are doing really well. I'm trying, again, being home all of the time is so weird. So I'm like always want to check the chickens, but it's not really good to shine a light up into them like every day. I'm trying to take a break from that so that they can grow and be, you know, at peace. But they're doing really well. So I wish you guys would get to be able to see them in person, but I will absolutely live stream when they're hatching and record that, because that is like one of the coolest things I've ever seen. So I will make sure you guys get to enjoy that. I'll send messages out or I'll live stream it. All right. So no, don't worry. You'll still get to see the hatching process, and then hopefully we'll have more information about when we're coming back. All right. It looks like I made the image too small for you guys to be able to put the text in. All right, sorry about that. Really quick, I think it'll be a lot faster for me to do attendance than me trying to go back and forth. So I'm gonna unmute everybody so that when I call your name, you can just say here, and then that's way easier for me to count attendance for today. All right, so there's some people I know that were here that might have had to leave. All right, so I'm gonna unmute everyone, please. All right, Maria, are you here?
Here. My 4Gs, it came on.
Yes. Braylee, are you here?
Yes.
Thank you. Marcus, are you here?
Yes.
I don't see Marcus. Okay. Divinity, are you here? No Divinity? Avante, you're here?
Yeah.
Yay. Aaron, are you here?
Nope.
Aaron? No, Aaron. Okay. Jakaya, are you here? No, Jakaya. All right. Samara, are you here? Yes. Sharika, are you here? Yes. Taylor?
Yeah, I did.
Yes, Taylor's here. Alasia?
Yesterday.
It's Chucky.
No, Alasia? Zoe is here. Yay. Christian, are you here?
Yeah.
Yay. Are you?
I want to see chickens.
Riley, are you here?
I want to see
Obviously.
chicken.
Sorry. Anna is here. I know that. Logan is here. I know that. Lakai is here. Hadrian's here.
Hey.
Hey. Mary. Yes. Kaylee is here. All right. Callie is here. Chris is here. Willie is here. I don't believe Pierce is here. Miles is here. Alice is here. Janaya. Yes.
I'm here. I'm here.
Chris Gadsden.
Me here. Me here.
Chris.
Chris here.
Yeah.
Yay. Samira's here. Blaze here. Letitia.
Here.
Yay.
Yeah, this is probably
Cody.
the one you said that. That wasn't.
Whoa.
No Cody. Aiden is
I know
here.
that. Oh, I'm
Andrew
sorry.
Lawson is
Remember the other day you said
Tiana is here.
that's must be 14.
Tiana's here. Noah is here. Christina is here. Lene is here. What's here? Arison is here.
Yes.
Alex.
I'm here.
is here. Ian, are you here?
You got anything?
I'm sorry.
Thank you. Adamaris is here, and then is Edward here? Yay! All right, everyone, you are fantastic. I'm going to stop our lesson for today. I hope that helped, and I'll see you guys tomorrow. All right, have a great day. Be active.
Wait, Miss Ryan. Miss Ryan.
Yeah.
What is the independent variable?
The independent variable was the number of clicks, the number of half-lives.
Oh. What's a dependent variable?
The dependent variable is anything in an experiment that you're recording is your data, and that's how you can remember data starts with a D, so it is dependent variable. So our dependent variable today was us recording the number of heads up, which were representing our undecayed carbon atoms.
Zoom is not working.
All right. If you are finished with your Nearpod lesson, I'm leaving it up so people can finish. Then we may go. And I hope you have a wonderful day.
I miss Ryan.
Bye. Thank you.
That's right. I found a really old coin.
How old is it?
I think it said 1745.
What? Are you serious?
I looked it up. It's I'll search it.
Yeah, you should.
Bye, Miss Ryan.
Bye. Thank you, everyone.
You want to say bye to my sister?
Yes.
Mari!
Oh yeah, I was gonna need to get up now. So.
All of my pennies I got today from the bank, and they're all
Nuh-uh, that was fish.
2019 or 2020. No, I think they might all be 2019.
Mar.
Yeah, mine are all 2019.
When can we open the chips?
Open.
All right, everyone, I actually have to go to a teacher meeting, so I have to go. Please tell Lamaria I said hi.
The
Okay.
king on it ruled from like I think it said 1711 to 1727 to 1750 or something like that. I just searched it.
You know that coin's worth a lot more than its face value. Yes, we should keep that. Cool. How many? So did you get over 100 coins together?
What?
Did you have over 100 coins?
Yeah.
Yeah. All right.
But I counted out 100. So.
All right. Well, I hope this helped. It was different. All right. Ooh. All right, everyone. Have a great day. Thanks.